Okay, good morning, everybody. I think we'll start. Welcome to this plenary session. So we have one speaker in person and one speaker remotely, and we'll see how that all works. But hopefully you'll still be able to interrogate with them with your questions afterwards. Right, so the first speaker is Sasha Boltasseva, and she's from Purdue, and she's going to talk about advancing photonic design and quantum circuitry with machine learning. We will be run by the machines. So it's half an hour, and then we'll have 5 minutes of questions afterwards.
Thank you so much, Jeremy. And I would like to thank the organizers for giving me this wonderful opportunity to come back to the beautiful coast and to share with you some excitement that we have over machine learning. I guess like many of us right now, we are trying to see what really artificial intelligence can and most importantly should do for photonics at large. I will be reporting some results that I obtained at Purdue University, and that work is largely in collaboration with my colleagues, specifically and importantly with my dear husband Vlad Shalaev, but also with Professor Alex Gildashev and Sabri Kais. With my experience and most of the work over the past decade being in the area of optical materials and implementation of photonic devices, it was very interesting and exciting to venture into something which is quite new to our group, and nonetheless, we do hope that this is a critical development for the area of photonics, and that's where advances will actually be coming in the next years. May I ask to dim the lights a little bit because it's on the dark background. It's better if we dim them a little bit. Thank you. Oops. This slide advances seem to be working before. I'm sorry. Okay, so I'll start with a few words of motivation, and this is it's a shorter version of the seminar, so I'll try to go fast through all the steps of photonic process that we are going through, usually when we are looking into implementation of photonic devices. And then I give you a few examples of first advanced optimization of photonic structures. This means that we will focus on matter surfaces, specifically for applications in energy. And I will also show you advanced optimization for some more exotic application of photonic structures, such as in light sail, and on-chip photonic components for emerging quantum circuitry. Most importantly, I will be talking about machine learning, and then hopefully that would be the take-home message after today's plenary talk. And as I said, I will try to convince you and make it clear that it is absolutely crucial for us to implement machine learning essentially at each and every step of photonic process that we usually do. And what we usually do is to start with a concept, and this can be a waveguide or structure that you would like to implement, or it can be some structure where you want to study fundamental optical effects, and then you usually do numerical design, right? To do some numerical simulations, you see what dimensions, what kind of implementation is really feasible. You check which materials are available and do the fabrication integration, and finally the demonstration as well. So the logical way to think about where we really need and can use a lot of machine power is really at the design step. And here I appeal to the audience that has a lot of people doing inverse design. And this has been a wonderful tool in many areas of science, including photonics, where we actually, we sort of propagate back from the function that we want to get. We actually see what kind of design would give us this function. And inverse design is usually very computationally heavy. So here we have been working with machines, both in terms of direct calculation, but also in applying machine learning as well. What is also known and has been explored is to use machine learning techniques and actually optimizing very complex circuitry implementation when it comes down to a chip. So groups such as Helena Vukovic and many others that I will be talking about are applying both advanced optimization and some kinds of machine learning algorithms to actually see how we better optimize and functions on a chip and put everything together. What has also been applied in some areas of science is the application of algorithms for reconstruction of data, let's say from some sparse images. We have not been using machine learning much in helping us to analyze optical data, and there are several reasons for that. But what I would like to actually propagate to the auditorium today is that now we are at the point with quantum photonics emerging big time, where it is critical for us to use algorithms to recognize useful data in very low intensity signals. So we are dealing with single photon emission or emission of entangled photons, and the realization of measurement schemes that I will very briefly show at the end, where we use algorithms to recognize data from very sparse data sets, would be absolutely critical. And the last point that I would like to make, which is less maybe obvious, is that ultimately you would like your algorithm to be physics informed. And what this really means is that your machine learning algorithm is not really a black box as it is now, but rather it contains all the information and knowledge that we have acquired as a photonic community about both photonic concepts and huge photonic material database to actually give us an answer at the end, not only what kind of structure or shapes you have to make, but also what kind of materials you have to select for your specific structure. So let's start with the design stage. And as I said, I will use example of solving an inverse design problem. Inverse design problem is a known problem in computational photonics. So usually people use either evolutionary or gradient descent-based optimization in order to solve a multi-constraint problem. So you have a function, and this can be a specific spectral response, for example, that you are sort of propagating back in order to obtain what kind of structure will give you this response. One of the most powerful tools in inverse design that has emerged and that I will be spending time on, called topology optimization. Now, as a side note, this topology optimization has nothing to do with topological photonics. It's just a term that refers to optimization of shapes. And example that I'm going to use for you is how to optimize and how to develop a structure for a matter surface that works as a thermal emitter. So this is example from a sustainable energy where obviously photonics is playing a very big role. So here's a problem statement. You have a heat source, so this can be any heat source you can imagine. So it can be sun, it can be a burner, and the heat source essentially just heats the emitter. Here you can think about designing a broadband absorber as well, which we are very well equipped for. But what you are designing here is really a selective emitter that would reshape the emitted radiation in such a way that it is now efficiently absorbed with a photovoltaic cell. This concept is called thermal photovoltaics. And essentially it is, again, it's a redirection or re-emission of the radiation in such a way that it is mostly emitting in the band where it can be effectively absorbed. So if we look at the spectrum and how we spectrally talk about it, in the shaded region here, you have a working band of the photovoltaic cell. So this is gallium antimonide in this case specifically. And then the first thing that you are looking at is the black body radiation. Thing to notice here is that you have to go to really high temperatures in order to have some significant overlap of the emitted power with the working band of the PV cell. But what you care about is to actually optimize your emission in band. So this dashed line shows the ideal emitter. You want to emit everything in band and nothing outside the band, because the red part is just goes to heat or to waste ultimately. As many problems in photonics, this is a multi-constraint problem. So you can imagine that you have to take into consideration not only spectral features that you have to get, but also how robust it's going to be and what kind of materials actually can do the job. So people have spent a lot of efforts on both designing and implementing TPV structures, because it's theoretically actually promises very high conversion efficiencies. But as you can see that both the matter surface-based and photonic crystal-based emitters, we're actually utilizing very simple shapes. So it's something that based on a priori knowledge, and not something that you have optimized in such a way that you get unorthodox shapes. We have also started with a simple design. Before we go to the design, I would like you to look at this unit cell of the matter surface that we consider. And here we have a metallic mirror, dielectric spacer, and plasmonic antenna on top. One very important note is, as I already said, this is a multidisciplinary problem, right? So you have to optimize many, many things. And one of the things which is really a cornerstone of many applications in photonics is your constituting materials. And my group spent decades working on plasmonic materials that are robust enough to sustain high temperatures. And you see an example of a material that have a properties which is close to gold, but this material is really durable, and this is a material class representing transition metal nitrides, specifically titanium nitride, and I'm sure we'll hear more during this conference on titanium nitride as well. I have my former group team member, Nate Kinsey here, who spent a lot of time optimizing and working with this wonderful material as well. Okay, so you start with a titanium nitride disc on top of this mirror and a spacer, and you try to, just play around a little bit with the shape here. You won't get much improvements though. So if you want to get improvements in the spectral features and in your efficiencies, you actually have to look into more unorthodox designs and some very non-trivial shapes. And the access to non-trivial shapes is exactly applying the topology optimization. So topology optimization is a very powerful tool that has emerged from other areas of science, specifically civil engineering, to solve the problems of material distribution in space. Largely pioneered by groups of Ole Zygmunt, Ilya Blanovic, Stephen Johnson, Chang-Hui Fan, Helena Vukovic, and others. So this technique has been applied very successfully for achieving high efficiency designs for photonic crystals, waveguide components, matter surfaces, topological photonics, and many others. So you see immediately that this technique allows you to get into a realm where shapes are something unintuitive, right? So something that you won't be able to come up with yourself. So this optimization is really great. So we will talk about some constraints a little later, but one of the main problems here is that it gets computationally really heavy if you increase the number of parameters you are changing. So if you just change the shape, it works. If you want to change shape and the thickness, then you might be already in trouble. We'll talk about how to solve it a little later, but for now, let me just briefly show you example of optimization of this titanium nitride structure using the topology optimization. So essentially you select your figure of merit and you optimize the structure in such a way that you are actually optimizing the figure of merit or performance metric for your structure. So in our case, it's actually the in-band absorption over the out-band reflectivity. So you start with a quasi-random distribution, and then you have to converge to a binary mixture of your metallic structure, titanium nitride, with air. And you see that indeed you've gone far from a simple cylindrical structure to something which looks very unorthodox. And you get improvements both in the spectral response and the maximum efficiency. Let me give you another example where really using advanced optimization is crucial, and everything hinges on this multi-constraint and very advanced optimization. And this is a very far-fetched example of a breakthrough initiative, and that's where people want to send a light sail to the nearest star, to Alpha Centauri, with a message. This is actually a specific prize for a person who comes up with what kind of message we're going to send to those people or aliens that might be living on Alpha Centauri. So this is a great example of many different teams working together, and this is an international initiative. So this initiative deals with main topics that are related to communication part, laser arrays that will actually be launching the sail from the Earth, and the light sail itself. So the light sail part, the Starshot Light Sail Initiative, is led by Harry Atwater, and he leads a multidisciplinary international team of researchers that are trying to find not only the designs, but rather the right concept, the right materials to actually implement the light sail that would be extremely robust, mechanically stable, but also has the reflectivity and optical properties that are needed for the mission. So this is just an example. Again, it's our humble contribution to this tremendously hard and challenging, exciting initiative. It is a design of a grating that is made on a thin silicon membrane. And you see that, again, by using this advanced topology optimization, you can find the designs that will provide you extremely high reflectivity and provide the total mass, which would be less or around 1 gram per 10 square meters. This is exactly what you need for light sail. Another example that is becoming really crucial for the developments of the next level photonic structures is related to emerging quantum photonics. And my colleague and Vlad Shalaev will actually be giving both a keynote and tutorial on quantum photonics. So I refer all of you to his talk that will be talking about emerging area of on-chip quantum photonics, and a lot of practical implementations of quantum technologies actually hinges on the development of main components of quantum circuitry, and specifically single photon sources. And again, this is just a glimpse into the area and examples of structures that are now being explored as potential candidates for single photon sources on a chip. So you see that these are several works from several groups. So there's two papers from Igor Aharonovich group that is using emitters in hexagonal boron nitride, HBN, and trying to actually combine them with aluminum nitride waveguides, or using in a membrane setting. So you see the main challenge here is not only to realize a source of single photons on demand, but actually integrate it efficiently on a chip, because you really want to extract it efficiently and couple it into the on-chip waveguides in order to enable the future circuitry. Or the group of Helena Vukovic and others that are using different types of solid state defects and couple them to different types of photonic waveguides. So one thing that you would notice here is that there is not a single winning platform, right? So people are still looking into what would be the best candidate. And again, I would show you a little bit of intrigue here and say, refer you to the quantum talks of Vlad Shalaev to see what we think would be the winning platform for both single photon sources and for the circuitry altogether. But this is hybrid. Hybrid means that you will have to integrate dissimilar materials with dissimilar patterns and structures on a single chip and achieve high functionality. So just a single example that you can imagine needs optimization and advanced approaches here would be efficient design of a meter and position of a meter in such a way that it effectively couples to the integrated waveguide. So you can imagine that, again, not only the geometry itself of the cavity around a meter needs optimization, but also there are many ways of architectures to be constructed. So you can have HBN layer with a meter on top of silicon nitride waveguide structure or the coupling area, or you can have it sandwiched, and depending on the architecture, you can have different designs that would perform better or worse. And what's also very important in this specific case for optimization is that you can design using topology optimization the structure in such a way that it will be robust, for example, for the position of your meter.
We're just going to stop a second to reset your talk so that the people online can see it.
Oh, I see.
I'm very sorry to do that.
Yes, no problem.
So we're just a
no
minute.
problem.
I just want to do that.
Yes, sure.
Comparte la testa.
Online, but not the punchline.
Okay, now can you try to go back on just to see if
Sure.
online it's working?
Oops, I don't know. This one is.
Okay.
Okay.
It is okay now, actually.
It's okay online?
Yeah, it's okay online.
Well, it's not advancing the slides now.
Yeah, exactly.
Oh, I
There we
see.
go.
Okay.
Yep, that's working.
It's working? Okay, nice.
Okay,
So
good, good. I hope no one lost me at this point. But we are talking about advanced optimization that we actually need for many, many purposes in photonics, both for designing metal surfaces, efficient waveguides and couplers and cavities. And topology optimization is a wonderful tool. One problem is that it's very time consuming and it gives you local maximum search. So what really happens in most of inverse design problems is shown here. You start with a random guess and then you actually converge to a local maximum. Instead, what you can do and what you have to do is actually to use machine learning, because it becomes computationally heavy if you actually want to introduce more parameters or you want to search a bigger space. You train your network on the set of designs that are optimized by direct optimization. And what you really hope for, and that's what we would want from our machine learning algorithm, is really to look at all this local maxima here and then find you the global solution. This is not an easy task, and we'll talk about it later, but I just wanted to showcase some of the groups and approaches that people have been applying machine learning for. So there are several things that are tricky in application of machine learning for photonic designs, because we really need a huge training set. And nonetheless, both generative networks and deep neural networks have been successfully applied for the design of many components, including matter surfaces, with many groups listed here. What we have started with, and there are many machine learning algorithms to play with, and these are like commercially available. This is called generative adversarial network. So what it does is that it looks at the training set, and again, your training set are just designs that are already optimized. They are high efficiency designs. And so it looks at these designs and then it generates something similar from the random noise. So I will not go into details of the algorithms, but then when it's trained, it will actually generate thousands of designs in less than a minute, compared to generating hundreds of designs in like 50 hours with a direct optimization. Okay, of course, after that, you have to refine it and make sure that your black box generated something which makes sense. Now, remember what I said in the beginning, that we actually want to converge to something which represents a global solution. So what you really care about is training your network or training your system, black box, on a training set, yet you wanted to find an outlier that you were not able to generate via direct optimization. Some algorithms are better than the other with this regard. So what we found works better is so-called adversarial autoencoder, which means that you're not working with design itself, you actually compress the representation into so-called latent space. So by reducing dimensionality, you perform much better search, and you can also introduce some limitations and some constraints into the latent space that actually makes it possible to search really fast, to search in hyperdimensional space. So you can actually introduce many parameters in optimization. Remember what I said, with direct optimization, it's hard to change several things. And what's most importantly, there are some algorithms that would actually allow you to inject some physics or understanding into it. So the bottom line and the goal here is actually to make sure that we will be able to develop algorithms that are physics informed. Instead of just looking for an outliers, we want our algorithm to actually be able to relate it in some way to the physics involved in what it is looking for. Okay, but this is in the future, that's what we hope for. But so far what we have is a tremendous improvement in calculation time. So from hundreds of hours to a few minutes with a fully machine learning algorithm. And then we also have improvement in the efficiency. So compared to the cylindrical geometry that we started with, we actually approach ideal emitter with all these techniques. Okay, so the next point that I would like to make here, and that is very important, is that obviously one can say that, well, classical machine learning still would give you something which is very similar to what you obtain with direct optimization. You just need more power. You know, if you have more computational power, you can just calculate more designs and you get your high efficiency. So that's why looking into really disruptive ways to find a global solution to optimization problem is critical. And we believe that the answer to that is really leveraging the design is in the semi-quantum or in the machines that we are starting to have around us. And by that, I mean a machine such as D-Wave, like quantum annealers, and also quantum simulators that are starting to be developed. So what the idea is here is that we would like to map the problem that we have in photonics, and this would be optimization problem of the design that I just showed, into a physical machine, into the physical solver. So essentially what you're doing is you're importing your problem into a physical solver. In the case of D-Wave, it's a system of coupled qubits, and then you just let it evolve into the ground state. And if you can read the ground state afterwards, this could actually give you a solution, a global solution to your optimization problem. So how it is done? Well, in order to be able to actually map the highly constrained problems into the D-Wave machine, into actual solver, you have to do several very involved steps. So this is a collaboration with our quantum algorithms team at Purdue, led by Professor Sabri Kais. But essentially one way, for example, is to map our problem into so-called unconstrained binary optimization, or QBA. And QBA is known to be very hard to solve problem. So this type of problem is, for example, pops up in optimizing the traveling salesman path or the max catch. So again, for those that are looking into hard to solve problems and those that can be and will be used for benchmarking of the quantum solvers, this is just one of the examples. So what we are doing here is we're first inputting our photonic optimization problem into the Kuber formalism. And then we are using the fact that the Kuber formalism actually has the same representation as the Ising model Hamiltonian, which means that if we know the coefficients that we found from our photonic optimization problem, then we can actually go in and encode a physical system of qubits by knowing the local fields and the coupling between them, and by evolving the physical system of qubits, again, we will be solving this minimization of our optimization problem via the evolution towards the ground state. There are several very critical steps involved here that I will skip. Well, specifically and importantly, that you have to get rid of funky shapes, you have to go to binary vectors, and then you have to assign your figures of merit instead of your designs to a binary vectors, and then build this correspondence, or mathematical correspondence between your binary vectors and figures of merit by training the factorization machine via regression model, and then relate them to the Kuber model. So I will be happy to chat about it later on how we really encode this set of binary vectors into this Kuber or Ising Hamiltonian. But I will just show the whole process. So this is our stellar student, Blake Wilson, who is behind playing around with the D-Wave machine. But essentially what this flowchart shows is that you start with the same training set that I showed before. You actually make a representation which is now a binary vectors, and then you train this factorization machine in this manner that your binary vectors now have figures of merit assigned, and you actually embed these parameters into the solver and let it evolve to the ground state and read it backwards. The important outcome, again, without going into details, because that's not my area, and again, I'll be happy to provide detail offline. What we see here is that we compare the number of designs that we started with in blue. So this is a number of designs and corresponding efficiencies. And in red is what the D-Wave machine actually gave. So you see that we are in the area of the outliers that I mentioned already a couple of times. We get the high efficiency designs that are not necessarily in the training set. And that's an indication that you might be propagating towards the global solution. So, so this is a comparison of the classical machine learning and those on a D-Wave machine. Again, the great speed up and actually the real improvement in efficiency. Okay, so another thing that I would like to briefly mention in the remaining of time is really how we advance measurements, quantum measurements that are critical for the implementation of hybrid quantum photonic circuitry, which we are now starting to see more and more, and that would be absolutely crucial for the practical implementation of quantum technologies. So as I already mentioned, we are dealing with extremely low signals coming from the single photon quantum emitters that have to be integrated on a chip in such a manner that we optimize the emission by coupling it with cavities, and then we make sure that it couples to the waveguides, and we have a full control of it. The very first challenge here is actually to find a good quantum emitter. And everyone working in the area of quantum knows that it is very hard. There are so many materials, and we can have a solid state defects, we can have defects in 2D materials, that all needs a very thorough characterization before we actually start to do any experiments with them. So, and again, those who know the area would agree that the challenges here is that, well, there is always a low probability of finding a suitable or good quantum emitters with high quantum purity that really emit one single photon and not 2 or 3 or more. And then the characterization time really takes a long time. So, and that's exactly where machine learning algorithms become critical. Yeah. And what I would like to show you very briefly is really the schematic of characterizing a quantum meter, where you usually spend around 20 minutes or more in order to get the second order autocorrelation function G2 that really gives you the purity. If it's below 1/2, it's a good quantum meter. If it's above 1/2, it's a bad quantum meter. And instead of doing that, what you can do is to train your classifier in such a way that you deal with measurements that are performed in just a snapshot. It's just 1 second. By eye and by doing a classical fit, you won't be able to see anything. So it's just a random collection of points, so to say. But by training classifier, you'll actually be able with high fidelity to tell whether it's a good or bad emitter. So this is just a flow chart of the process. So you train your classifier, you assign the labels to good and bad emitters, and then you will be able to actually advance this really rapid classification. And just a glimpse of what's coming up, this technique can be combined with or overlaid with a photoluminescence map, leading to super resolution quantum imaging that will actually give you both the speed up in terms of measurements and in terms of resolution as well. And summing up, you in future, and actually already right now, because future is near in the area of quantum photonics, will be able to apply and should be applying machine learning algorithms both for optimization of your photonic structures and shapes in the way that I already showed, but also at many, many steps of the process, starting from characterizing your emitters, putting together all devices together, but also advancing new ways of exploring quantum material and enable quantum imaging. With that, I would like to put this flow chart again. And I do believe that machine learning will enter every single point of a photonic process. And I'm thanking the whole team, funding, and you for your attention. Thank you.
That's great. So we have time now for a few questions, which we encourage. There's a question in the middle here. If you shout, then maybe Sasha can repeat it.
My understanding of all machine learning is the large data set.
Yes.
Generally, those data probably is very
Yes, yes. And you are absolutely right. I didn't have much time to talk about it, but this is one of the problems. The reason we haven't been applying machine learning largely in photonics is that in order to generate large enough training set where it makes sense, you need a lot of computational power. Now, you don't have to generate a lot of data in order to train your network, because what you can do, you can actually use physical considerations in order to expand your training set. This is what I call physics-informed machine learning. Now it relates only to the training set, but it's very important. Like in our case, instead of generating tens of thousands of designs, which would take forever, you generate maybe several hundreds of designs. Topology optimization is built in such a way that each design that you generate is robust towards perturbation of sizes. So when you generate the design, you know that if you dilate your design a little bit, it would still be high efficiency design. So you can perturb your design a little bit, and this will expand your training set. That's one thing. The second thing that you can use symmetry considerations. You know, for example, that if you change the symmetry of the structure, it would still perform well. So these are things that can actually extend your training set tenfold. And that's what we have to use. It has to be physics informed. Yes. Yes, exactly. So the first set that I showed, that was only design. Now we have not been fabricating the structure. With this set, we still have fabrication constraint there. So the structure is again robust and can be fabricated. And the second part for emitters, it's experimental. So for example, we had like a 100 emitters. So we used 20 emitters to train our classifier. So how it is done, you actually do both the long measurements and the short measurements on all the 20 emitters. So but you know the ground truth, you know whether it's good and bad. This is how the classifier is trained. And then you can use this classifier for the rest 80 emitters to do just 1 second measurements. So we tested it experimentally. The same for the imaging as well, that it gives you a higher resolution.
So one final question down here.
For the data set, you said you fit in basically the best solutions you have, but is it really necessary? Why machine learning cannot learn on a random choice of parameters? Why should know optimal solution?
Well, you mean in machine learning to start with a totally random guess? Well, I guess in this case, well, first of all, again, you have to do the training on something which is already high efficiency. Otherwise, you will have to have like a combined structure where you have a direct solver and machine learning, right? Because you have your training set, or you have your design, and you have your function that you're optimizing, right? So the so it has to be a hybrid in a way, because otherwise, even for machine learning, it will be too hard. You know, with direct optimization, you cannot start from the random guess, because it's simply, you still have to inject a little bit of physics into that. I just feel that it really has to be physics informed in order to be efficient, because otherwise you can either end up in something which is like highly unstable or like unphysical, or it will just be stuck somewhere where efficiencies cannot be, you know, very high. So it has to be hybrid.
Okay, so I can see that there's going to be more discussion, so I encourage you to come and talk to Sasha in the poster session and the break after the next talk. So let's thank Sasha again.
Thank you.